Hi everyone, welcome to our next video for week 4 on another type of hypothesis test for a contingency table called a test for homogeneity. A test for homogeneity of proportions is used when samples are selected from different populations and the researcher is interested in determining whether the proportion of elements that have a common characteristic are the same for each population. For example, I could be interested in the proportion of specific colors of M&Ms and Skittles and comparing whether those proportions are the same for M&Ms and Skittles. The different populations would be the two different types of candy. And then the common characteristics would be the colors that those two groups have in common. The hypotheses for a test for homogeneity of proportions are always the same, which is nice. The null is that the proportions are equal, and then the alternative is that at least one proportion is different. Everything else about this test is going to work exactly like a test for independence, which we saw in our last video. We're going to be using the same function calls. We're calculating expected values the same way, which our calculator is going to do for us. So this is very similar to a test for independence with just a change to our hypothesis. A quick reminder before we move on, just like every other hypothesis test we've done, you should, during that step 1, identify which of these hypotheses is the claim that we're interested in testing. It doesn't affect how we carry out the test, but it does affect how we phrase our conclusion in step 4. So quick review of the p-value from the test for independence. You can see here we have the formula for calculating the expected values for each cell in your contingency table. I've noticed a couple of you have been doing work by hand, and if you want to do that, that's fine. You should show this off to the side of your table. However, you don't need to do this because both GeoGebra and the TI-84 will calculate these expected values based on the observed values that you feed it. So don't let this formula scare you. You don't have to use it if you don't like doing calculations by hand. Okay, so for the TI-84, to find our p-value, we need to enter our observed data in a matrix. We want to enter the data exactly as it appears in our contingency table. So second, and then the x to the -1 button. You're going to move over to the edit menu and select that first matrix named A. When you press enter on that menu option, it's going to pop up the name of the matrix and then the size of the matrix and the matrix itself. So that next step is to enter the number of columns and number of rows followed by enter. And it actually wants them backwards. It wants rows first and then columns, which makes sense because that's how we use notation for our expected values. And then you're going to press enter after you've done that, and it's going to move you into the matrix. And then you're just going to enter the values from the table, pressing enter to move to the next value. Once you've entered that last value, you go back to your stats menu over to test, and you look for option C, the chi-squared test. You should not need to change anything here. You should be able, once you've got the chi-squared test open, go down to calculate, just press enter. The calculator should default to the observed being in A and the expected output going into B. For GeoGebra, similar idea, except it's not going to output the expected values. First step, you create your matrix of observed values. So you're going to give your matrix a name and then double curly brackets. So you need outer curly brackets for the, outer curly brackets for the matrix itself. And then each row goes inside those outer curly brackets as a regular list. So curly brackets and the number separated by commas. Once that matrix information is entered, you're just going to call chi-squared test with the matrix name. So we're going to go ahead and do some examples together. I'm going to do one with the TI-84 and one with GeoGebra so you can see how both of those work. So for our first example, do male and female college students have the same distribution of living arrangements? Use a level of significance of 0.05. Suppose that 250 randomly selected male college students and 300 randomly selected I should say 300 randomly selected female college students were asked about their living arrangements, dormitory, apartment, with parents, or other. The results are shown below. Do male and female college students have the same distribution of living arrangements? So we can see in our data table, we have our two different populations, males and females, and then we have the four categories they have in common: dormitory, apartment, with parents, other. And we're asking if the proportions in dormitory are the same, proportions in apartments are the same, proportions with parents are the same, and proportions in other living arrangements. This test, if we reject the null, will indicate that at least one of these proportions is different. It will not tell us where that difference is. So this is just going to tell us, are the proportions the same or is there a difference somewhere? That's a common theme. We're going to see that again next week when we talk about a process called ANOVA. Let's go ahead and switch screens here so we can do our work. So we know the first step for our hypothesis test is to state our hypotheses, null and alternative. We know for a test of homogeneity of proportions that are the proportions equal, P1, P2, P3, P4. And then the alternative is at least, sorry, I can't write today. At least one proportion is different. And then looking at that last sentence, it says, do male and female students have the same distribution of living arrangement? So they're using that keyword same. So we're up here. Whoops, not same, claim. This is the claim we are testing. For step 2, we're going to find our p-value method. So we have one of two choices. I'm going to do TI-84 here. I know TI-84 needs to know where I put my observed values. So I'm going to say my observed values are going into A. The other thing we need, degrees of freedom, and ultimately an alpha, which we'll get to at the next step. So that degrees of freedom, we know for contingency tables that our DF is rows -1 times columns -1. So for this test, we have 2 rows, and then we have 4 columns. So 2 minus 1 is 1, 4 minus 1 is 3, and 1 times 3 is 3. So degrees of freedom is 3. And then we're going to call for the TI-84 chi-squared test. It's going to ask, where is our observed and where do we want the expected? So let's go ahead, pull up our calculator and do that really quick. So second, x to the minus 1, we go to edit, enter. In this case, I have 2 rows and 4 columns. And you can see that now my matrix is the right length, and then we're just going to enter our values. And you'll notice the whole matrix doesn't fit on the screen. We can use that arrow key to scroll back and forth across and check that we entered those values correctly. Once we've got the values in, we go stat, tests, and down to option C, chi-squared test, and then we go down to calculate. And so here we get a p-value of 0.0175. 0.0175. For step 3, we're going to make that comparison, p-value to alpha. We know when we're not given an alpha, we assume 0.05. In this case, they actually did here. Alpha is 0.05. And then 0.01 something is definitely less than 0.05. So I'm comfortable rejecting the null. So for step 4, we rejected, so there is enough evidence. And then our claim is the null, so we're talking about rejecting. So there is enough evidence to reject the claim that the male and female college students have the same distribution of living arrangement. So this tail end, I'm pulling right here from the word problem itself. Reject the claim that male and female college students have the same distribution of living. So we know for these, at least one of these is different. Let's go ahead and move on to our second example. The example 11.9 says, both before and after a recent earthquake, surveys were conducted asking voters which of the 3 candidates they planned on voting for in the upcoming city council election. Has there been a change since the earthquake? Use a level of significance of 0.005. The table below shows the results of the survey. Has there been a change in the distribution of voter preference since the earthquake? And you can see they've given us a table of before and after for 3 candidates for an upcoming city council election. So we're going to go ahead and jump into our hypothesis test. I know before I do that, I need to identify my alpha, 0.005. I should calculate my degrees of freedom. Rows -1, columns -1. So in this case, we have 2 rows. We have 3 columns. So 1 times 2 is going to be 2, very small degrees of freedom. So similar to last time, in this case, 3 proportions, P1 equals P2 equals P3. Oops, I should label that, sorry. Each one is at least 1 proportion is different. in this case, we are testing the claim, has there been a change? So for this one, our alternative is the claim. Let me go back and fix this. The last book I used called the alternative H1, so I'm kind of been defaulting to that, but our book uses HA. Sorry about that. Okay, second step is p-val. This time we're going to use GeoGebra. Same idea, we should tell us where is our observed data. So here's the observed frequencies. And then I'm going to call this matrix M. For GeoGebra, I don't need an output matrix for the expected values. I'm going to list my degrees of freedom. And then we're going to call chi-squared test. And all GeoGebra wants is the matrix name. So let's go ahead, pull up GeoGebra and enter this information in a matrix. M equals outer curly brackets for the matrix, and then inner curly brackets for each row. So our first row is 167, 128, 35. I'm going to move out of those and then comma, and then a second list, second set of curly brackets for the bottom row. 4, 97, 225. When we hit enter, it puts it in matrix form. So that looks like the data looks in our table. That's a good sign. And then we just call the function. So chi-squared test, and give it the matrix name, and it gives us both the p-value and the test statistic. We want that p-value of 0.1959. 1959. So step 3, we're going to make our decision. We compare that p-value we just found to our alpha, 0.005. And 0.1959 is much bigger than 0.005. So our p-value is greater than our alpha. So we are not going to reject. Do not reject the null. When we fail to reject, our conclusion in step 4 starts with there is not enough evidence to. Then we go back to step 1. The alternative was our claim, so we're talking about support. So there's not enough evidence to support the claim. And to fill in the rest of that sentence frame, we go back to the word problem, and it says, has there been, so the claim that there has been a change in the distribution of voter preferences since the year. Okay, so hopefully that feels familiar. I'm hoping that feels a lot like those tests for independence we saw in the last video. If you have any questions, feel free to shoot me an email or text message. My contact information is on Canvas, or drop by my office hours on Tuesday, Thursday, or Saturday. A note about Tuesday, I have a meeting in the afternoon, so I'm going to cancel my afternoon office hours and just do extended office hours on Tuesday night. So I'll be available from 6 to 8 on Tuesday, and then regular hours on Thursday. And then I also have extended hours on Saturday from 2 to 5, because I know this material can be a little bit tricky. All right, I hope you're having a good week, and I will see you in the next video.